Hello and welcome back for a final time to this 8-bit CPU here. And so today we're going to finish looking at the microcode, which is programmed into these EEPROM chips here, which make up the control unit of this CPU. And so in the last episode we started looking at that microcode and we looked in detail first at the microcode for the various move class instructions that our CPU supports. So those include a move from one register to another. They also include instructions such as this one, which move an immediate operand, which is simply a value embedded inside the program text into a register. And they in fact also include instructions such as this jump, or even conditional jumps. So we encoded all of those, also this halt instruction, as move class instructions. That means that the first two bits of their opcodes are 0, 0. Now in this episode we're going to look at the microcode for the rest of the instructions that our CPU supports. And so we divided those into the three remaining classes. We have broadly we have the load class of instructions, and so they have 0, 1 in their first two bits of the opcode. We have store class instructions, and so they have 1, 0 in the first two bits of the opcode. And then we have ALU class instructions, such as this increase instruction, and they have 1, 1 as the first two bits in their opcode. So all right, at the moment the CPU, I've loaded this program into the CPU, and this is in fact the same program that we used in our episode about the RAM module here. And the reason is that it contains lots of very simple memory operations, such as load and store, and also contains this ALU operation, and so it will allow us to have a look at those instructions in detail. Now, at the moment, the program counter has a value of 2, and our micro timer here is at time t0, so we're just about ready to start executing the instruction at address 2, which is this load instruction. So what that's supposed to do is to look at the D register, which is down here, and currently contains a value of 2, and it should use that 2 as the address in RAM, and so read the byte which is in data memory at that address, in this case 2, whatever the contents of that register are. And then once it's read out the value from RAM, it should write that into this register, and that's in this case that's the A register, so it'll show up here on this digital display. And so that's what that instruction ought to do. And so as for any instruction, the first two signal words or first two bits of microcode are the same for time t0 and t1, and they just fetch this opcode and insert it into the instruction register. So we'll go through those very quickly. So that was time t0 and that was time t1, and so now here in the instruction register we have this load instruction, or at least the opcode for that load instruction. So since we want to access data at the address which is currently in the D register, the first thing we need to do is to get the contents of the D register into the memory address register, so we can point there. And so what we need to do is enable the D register onto the bus, which is what this control signal achieves. And then subsequently we need to write that into the memory address register, which will happen on the next rising clock edge. And so for time t2, the microcode for this load instruction needs to assert these two signals. So some enable signal on whatever register we are dereferencing, and then the memory address write signal so that we point the RAM at that address. And so that's all that the time t2 needs to do. So all right, that value is now in the memory address register, and so on time t3 we can then enable RAM because we've set the address register for the RAM to point at the address we're interested in. Since we're simply loading, we want to load from data memory, so we won't be asserting the program memory signal, so that stays off. But of course then we need a corresponding write signal for whatever register we want to load the value from RAM into. So in this case that's the A register, and so the A register write signal is being asserted. And so the microcode for time t3 for this load instruction is a memory enable and then a write signal for whatever register we want to write to. And since this is the last microcode piece for this instruction, we are also asserting the timer reset signal. And so that will complete this load instruction. So this value, which is this here, will get loaded into the A register. So that's a load instruction. Now a store instruction, this next instruction happens to be a store instruction. So once again, we're at time t0 and we're at address 3. So we're now nicely pointed at this store instruction. So again, the first two microcycles are the same. We need to get the instruction from program memory, which is at this address, and then load it into the instruction register. But then now we can have a look at the microcode for the store instruction. And so the store instruction, what it will do is it will take a value from some register and it will then write whatever is in that register to a specific address in data memory. And the address where this value should be written is in another register. And so once again, the first thing we need to do is to point the memory at this address. And so we need to get that register out onto the bus. And so the D register is enabled onto the bus, so that value goes onto the bus. And we need to write that into the memory address register. And so that value will go into the memory address register on the next rising clock edge. And so that's the microcode for time t2 for the store instruction. And then on micro time t3, what we need to do is we need to get the contents of whatever register we want to write into RAM. Now in this case, those were both the D register, but they could be any combination of registers. So that register is enabled, the one which we want to write into RAM. Onto the bus, and then subsequently we have a memory write signal, so that the RAM, which is now pointing to the correct address because we set the memory address register, will take the value which is on the bus and write it at that address in RAM. Now this is the last microcode signal word for the store instruction, and so we're also asserting this timer reset signal. And so that concludes the store instruction, and so now this value of 2 is stored in RAM at address 2. And the next instruction in our program is this increase instruction, which is an ALU instruction. So we're at address 4 right now, and so we're at this increase instruction. So again, time t0 and time t1 are always the same. We need to get that address into the memory address register and then get the opcode into the instruction register, and so there it is. And now this is an increase instruction. And so what we want to do for an increase instruction is, we saw that in the episode on the ALU. In fact, what we want to do is to get the contents of that register, which is the D register. So we're enabling the D register onto the bus. So there it is. And by enabling it onto the bus, that will automatically become the A input into our ALU. And for an increase, we want to set the B input to be 0 and then add, actively assert a carry in to our ALU. And by doing that, we will achieve the calculation of the value of the A input of the ALU plus 1, and the B input will be set to 0. And so the control signals here, you can see the B input is not being asserted, and so that means the B input isn't coming from the B register, but is instead hardwired to 0. But we are actively asserting the ALU carry in signal. And so we will be adding a 1 to whatever the ALU is calculating. And then here are S signals, which we read back to front, remember. So S2, S1, S0 are set to a low, high, high, which corresponds to an A plus B operation. And so the result of that calculation will, in the first stage, be stored into this ALU register, which we have here. So the ALU register write signal is also being asserted. And so those are all of the control signals which the microcode needs to assert on the time t2 of this increase instruction. And so when we execute that, this ALU will in fact latch the value of 3. And now that won't carry, so none of these flags will come on. But then here we have the final microcode for the increase instruction. So on time t3, we now have this value which we just calculated into this ALU register. And so now that the bus is free, we're no longer asserting the D register onto it. We can actually enable this ALU register onto the bus. And so that 3 is now onto the bus. And since we're increasing a register into itself, we then need to assert the write signal for this D register so that the contents of the ALU will be written back into the D register. And this is the final step which we need to perform in order to complete this increase instruction. And so we've also have the timer reset signal here, which is asserted. And so if we, on the next rising clock edge, we will complete the increase instruction. And so there we have this 3 now. So starting again in our microcode programmer here in our Arduino development environment where we left off the last time. So we finished looking at this function here which writes all of the move class instructions. So now we'll start looking at the load class instructions. So the first set of instructions are in fact the simple load instructions, like the one we just looked at. And so they will take some value in a register and use it as an address register. And so point memory at that location and then read out the contents from memory into some other register. And so the source register is in fact is an address register, and the destination register is a data register in this case. And so as we saw, the microcode which we need to accomplish such an operation has two steps apart from the fetch cycle. And so in the first step, which is on T2, after the fetch has been completed, we need to enable the source register onto the bus, and then we want to use the value in that source register and write it into the memory address register so that we point the RAM at the correct address. And then in the second microcode step on time T3, ignore this for the moment. We want to enable the memory itself so that the value from the memory goes onto the bus, and then we simply want to write that into whatever destination we've chosen in our instruction. And so we want this particular microcode to be written for every possible combination of physical registers from A, B, C, D to the stack pointer in the program counter. So we have this double loop here, and so by going through all of that we will have written all of the possible load instructions. Now, to get back to this little operation here, so in general, this instruction is used to read data memory. But there may be particular circumstances in which you will want to read a byte from program memory. Now, of course, many instructions do that automatically. For one thing, the fetch cycle always reads from program memory when it goes to get the instruction. And of course, any instruction which is referencing an immediate operand will also access program memory, because immediate operands are located in program memory inside the program text. But to make sure that our programming environment remains sufficiently flexible, we do want to give the programmer a possibility of reading some random location inside of program memory. And so what I've done here is I've given special meaning to the C register. And so if the source operand here, if we are dereferencing an address in the C register and only in the C register, then I will in fact assert the program memory signal in my microcode. And so if we ever want to read some data which is located in program memory and which we can't read simply by using immediate operands, or if it's not part of an instruction, we could, for example, have a function pointer table or something like this somewhere in program memory. And then in that case, we might actually want to, there might be legitimate reasons to read data out of program memory. And so we can do that by making sure that we write the address into the C register, and then we can say the load instruction, which is dereferencing the C register, has this special meaning that it will in fact dereference program memory and not data memory. So that's the reason for this here. Now, ignoring this pop instruction just for a moment, we'll get to that later. We'll have a look at these instructions. These are load instructions where the address we want to load from is not in some register, but is in fact an immediate operand. So what we need to do is first go and get the address in program memory, then load that address into the memory address register, and then finally read out data memory into this register, into the destination register. So as we can probably guess, that will be an operation that requires 3 steps of custom microcode. And so the very first thing we need to do is we need to dereference the program counter. So we need to enable the program counter onto the bus, because that will now be pointing at this immediate value in program memory. We need to get that program counter value into the memory address register so that we can point memory at that immediate operand. And of course, we also need to increase the program counter, because once we've read that byte, we need to actually point the program counter at the next byte, which will be the next valid instruction. So these are the first, this is the first microcode instruction for this, this particular load instruction. And so on time t3, which is the next micro time, then we need to enable the memory. We need to make sure it's program memory, because we're actually fetching this immediate operand. And we need to store it into the memory address register, because that is in fact the memory address from which we want to read a byte in data memory into our final destination register. And so our second micro instruction here is to enable memory from program memory out into the memory address register. And so we write it in there. And then finally, on time t4, we will enable the memory once again, but this time not program memory. We will be enabling data memory. And then we want to write that to the actual destination register, which we encoded in our instruction. And so this is the microcode which corresponds to such a load instruction. And so we want to make that possible for all possible physical registers. So once again, we loop from the A register all the way to the program counter. And so assuming that we also handle these pop instructions, which we'll get to in a moment, that basically is the entire list of load class instructions that our CPU will support. And so any other combination of bits in an opcode, where the most significant bits correspond to the load class, i.e. 0, 1, well, we consider those to be illegal instructions. And in fact, those are any instructions where we are loading into the immediate operand or loading into this stack pointer with auto increment operand. And so as we've discussed in previous videos, that instruction really only makes sense if this particular register only makes sense if we're dereferencing a memory location. So we can't actually load into or store from a stack pointer with auto increment. And so we consider those, so anything with a stack pointer, auto increment, or an immediate destination operand for any kind of source register, we consider to be an illegal instruction. And so because we don't have a specific illegal instruction trap or exception handler or anything like that in our CPU, we simply halt it using this very simple microcode here of exactly one cycle, which simply asserts the halt signal. Now the various store class instructions work in a very similar way. And so the basic store instruction, which we had a look at in the beginning of this video, takes the value from some physical register and stores it into data memory at a location pointed to by some other physical register. So in this case, the destination register is considered to be an address register, and the source register is considered to be a data register. So the opcode for such an instruction is in the store class, and so destination and source registers are simply the 3-bit values which we've assigned to those registers. And the microcode for such an instruction contains 2 steps, as we saw. And so in the first step, we want to enable this destination register address, which we will then write into the memory address register, so we can point the RAM at the address to which we want to write the data in the source register. And then in the second step, which corresponds to time t3, we will enable this source register, the value, straight out onto the bus, and then simply write it using this memory write signal. Now notice that in the case of the load instruction, we allowed this address register, if it were the C register, to in fact point to program memory. But we really don't want to ever write into program memory. That's we're not into self-modifying code, and that's generally a bad idea. So in my CPU, I don't allow that. And so in the case of this store instruction, we don't ever access program memory. And so the only way to ever write anything in program memory is to manually use the dip switches and this programming toggle switch, which we have. So we don't support modifying anything in program memory. Now again, we'll come to the push instruction in a little while, because just as the pop instruction, it's a combination of a memory operation and an ALU operation. And so we'll have a look at the ALU operations first, and then come back and look at the pop and the push instructions. But so we, again, for a store instruction, we can also have the address to which we want to store information in an immediate operand. And so we can do that using this kind of a store instruction. And so again, in this case, what we need to do first is to go and get that immediate address from program memory so that we can write it into the memory address register. So that the memory then is ready, pointing at data memory at this location, and we can actually write the value in this source register into that location. And so we have here microcode, which consists of 3 instruction cycles. And so in the first one, we need to get the contents of the program counter, which are in fact already pointing at this immediate operand inside the program. We need to get that into the memory address register, and at the same time increase the program counter so that it now points beyond that immediate operand, and it's in fact pointing at the next instruction. And we then want to read out from program memory, so we enable the memory and we enable this program memory signal, and we want to read the contents, which are this immediate operand inside the program, directly into the memory address register, so that we can then in fact write into memory at that location. And so that's what happens in this last signal word here. So we enable the contents of the source register, which we actually want to write into memory, and then we activate this memory write signal. And so that will write into the correct location, which we loaded into there with the previous 2 cycles. And so that's what we need to do for a store instruction where the address is in an immediate operand. Now, once again, we have a whole series of defined store instructions or store class instructions, and so we've written all of those. But then there are certain combinations of register input or output values which we don't support for store instructions. And once again, anything with a source register, which is either this automatic increase stack pointer or an immediate operand, we don't support. And no matter what the destination register. And so for all of those, these are in effect illegal instructions. We once again we simply instruct the CPU to halt, which is what we do because we don't have any kind of exception handling. Now, in the episode where we talked about the ALU, we finally determined all of these ALU instructions that we are going to support in our CPU. And we also figured out which control signals that we need to activate for these various ALU operations. So in fact, we more or less already did the work of constructing the microcode which we're going to need for all of these operations. And so in each one of these operations, the sequence is always the same. So we need the ALU to perform some sort of calculation, and we do that by setting the ALU S0, S1, and S2 signals, as well as the ALU carry in signal and the ALU B signal to whether we want the B register or simply a hard-coded 0. And then this A input is always connected to the bus, so we also need to enable some register onto the bus. And so that is the first microcode cycle for any ALU operation. And then of course we need to write that into the ALU register. And then the second cycle is always going to be to simply read the contents of that ALU register and then write them to wherever this instruction needs the result to be written. Note that some instructions, for example this compare instruction here, don't actually need to write out the contents that we calculated. All we're interested in this case are the flags. But of course what we didn't do when we talked about the ALU is determine an opcode for these various instructions. So that's the last thing we still need to do in order to fully define the ALU's operation. We need to invent opcodes basically for all of these instructions. And so, all right, here is that same table, and we've added an opcode column here for a basic opcode structure for each one of these instructions. Now, perhaps you'll remember from our discussion when we were talking about the general architecture of our ALU, we came to the conclusion that since we have to encode them basically in 6 bits, because these first 2 bits will be set to 1, 1 to say we're dealing with an ALU class operation, that left us really with 4 bits to encode the operation, and then 1 set of 2 bits to encode some register, and so we decided that meant the second register in fact always had to be the B register, or we had simple single operand instructions. And then the first register would necessarily be one of the general purpose registers, A, B, C, or D, and so we couldn't use the program counter or the stack pointer as an input to any of these ALU operations. But then, in fact, we never actually defined the 4-bit opcode which we would assign to each of those instructions. And so what I've done here is come up with a scheme which is sort of a little bit systematic, especially for these basic operations. And so you'll remember that this S signal, this S2, S1, and S0 signal, which we are sending, these control signals which we are sending to the ALU chips, that they actually correspond directly to this input signal which our ALU chip, the 74LS381, expects. And so it defines a whole series of operations here, and so we can select one of those operations using some combination of these 3 bits. And so I've basically gone with that as say these 3 bits here. So the A plus B operation, which is in fact what we want to do in the case of an add instruction. Well, that's the 0, 1, 1 combination of S bits. That's in fact the same as that. The subtraction operation, so that's A minus B. Well, that corresponds to 0, 1, 0. And for example, the AND operation here, that corresponded to 1, 1, 0. But then, of course, we have this 4th column, and I've sort of, gone with the convention that we'll set that 4th bit to either a 0 or a 1, depending on whether we want our ALU operation to take into account the previous carry or not. And so this add, this will always set the carry in to 0. That won't take into account the carry output from the previous operation. But this instruction, which for the ALU is also an addition, but will actually set the carry in depending on what the carry was of the previous operation. Well, we'll encode that by setting this bit to 1. So of course that works very well for addition and subtraction. And in fact, if you'll remember, our ALU supports 2 kinds of subtraction. So we can subtract the first operand from the second operand, but we can also subtract the second operand from the first operand. And so, as it turns out, we can actually support 2 different kinds of subtraction. Since one of our operands always has to be the B operand, but since the subtraction operation isn't commutative, well, we can actually also support subtracting some other register from the B register, and then writing that result back into that other register. So we actually also can support such subtractions, which are different from these. And so we'll encode those using the corresponding 3 bits also from our chip here, from our 74LS381. So we'll be using the B minus A encoding, which is 0, 0, 1. And so we'll use that for our opcode. I mean, it's as good as any value. And once again, we can do it once with the carry flag, with taking into account the previous carry or not. Finally, remember that for subtractions, because of the way our ALU works, if we don't want to borrow, which is what you do in the case of a subtraction, then we actually need to set the carry in to 1, because the carry in turns out to be exactly the opposite of the borrowing. So one thing to remember here. Now, of course, that doesn't really work for all operations. So for example, these logical operations here, AND and OR and exclusive OR, so okay, we can set our opcode to a 0 here in the carry, whether we want to take into account the carry or not. And then we can set our operation code here to A and B, or A or B, or A exclusive or B. And so these are indeed the values which our chip defines here. But of course, there is no such thing as an AND with carry, because an AND never produces a carry out, nor does an or nor does an exclusive OR. And so the result of that is that we actually have 3 extra possible opcodes here, which we're not using for AND, OR, and XOR operations. And so in this case, for example, I'm once again hijacking one of these opcodes which we don't use for its official meaning, and assigning it a totally different meaning. So I'm using this AND operation to actually mean compare. And so in this case, these 3 bits, in fact, correspond to this AND operation, but that doesn't matter. This is just an opcode. I'm just finding some space for this compare instruction somewhere in the opcode space. The actual operation, the actual signals which our microcode will have to produce will of course not be A and B, it will be this combination of input signals, which is what we need in order to perform a compare operation. And so there are a number of instructions that we can encode in that way. Now, one operation you'll remember that our ALU chip doesn't natively support is the NOT operation. And so we saw that in order to achieve that, we need to set, we can actually do it by you know, a correct combination of input signals and operation signals. But to encode it, we need to find some other scheme. And as it turns out, these 3 bits here, which we use to encode the operation, and so far we've been using you know, the same values that this chip wants us to use, just to keep things simple. There are in fact 2 combinations of 3 bits which this chip doesn't use at all, or does use but we don't use those ever. And so low, 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 as you can see, is not used at all by this chip. And high, high, high is used, which is 1, 1, 1, but we don't ever actually use that operation because it's not useful. It simply presets everything to high. And so we can use those in our opcode to once again hijack them and mean something else. And so we've assigned meaning to these combinations 1, 1, 1 and 0, 0, 0. And so the 1, 1, 1, well, I've assigned that to the NOT operation. And so a NOT, although inside the ALU will be performing some other operation, in our opcode space, well, we can use that combination of 1, 1, 1. And so a NOT with carry, once again, would be a logical operation, and there's no point in looking at the carry flag for logical operations because it's never set. So we can assign that a different meaning as well. And so I've defined a new instruction here, which is a test instruction on a single register. And the idea of that is basically to compare a register to 0. And sometimes that's useful. In particular, we might want to see if the register is negative or if it's 0. And then we can do that. We could say test some register, and then immediately after that we could have either a jump 0 or a jump negative, for example. That could be a useful sequence of operations. So we can define such an operation by redefining a NOT with carry as in fact to be a test. And it turns out that what we need to do in order to do that, so we really, just as in the case of the compare instruction, all we want to do is set a series of flags. And so we can achieve that by, in this case, adding together the original register with a 0. So the result of that will be the original register. And so the flags, and if we also set the carry in to 0, then we really will get the value of that original register. And the flags will reflect whatever is in that register, whether it's 0 or negative, etc. And so now we have this increase and decrease instructions. And so here we use the other combination of 3 bits, which for our chip here have no meaning. And so for our opcode, once again, that gives us some free space, which you can use to assign somewhere else. And so in this case, I've assigned those to the increase and the decrease instructions. And so the increase instruction is, okay, it's all zeros here. And so that's an operation performed on a single operand. And we already determined, when we looked at the ALU, that these are the actual signals which we need to send to the ALU in order for it to perform that increase. But so in our opcode space, we'll assign it to this operation code of 0, 0, 0. And the decrease instruction, well, I've simply determined that I've reassigned the meaning of increase with carry, which doesn't mean anything, because that would in fact be an increase by 2. And okay, that's not an operation we want to support. So I've reassigned another meaning to that to actually correspond to the decrease instruction. And so again, for the decrease instruction, we've already determined what we need to do, what we need to send to our ALU. But so in our opcode space, we'll simply assign that to this operation code, but then with a carry set to 1. And then finally, the push and the pop operations, well, we're not assigning those opcodes in the ALU space. We're assigning those into the store and the load spaces. And so we don't need to worry too much about the opcodes. So we've already taken care of those. And so coming back to our microcode program here in the Arduino editor, and at the top of our file, we've defined constants which give us these 3-bit codes corresponding to the various operations. And so these are operations which are actually defined by our 74LS381 chip, and which we'll be using both to encode instructions, ALU instructions, and also to actually set signals in our signal word here, these ALU S0, 1, and 2 signals. And so we'll be using the same code. But then we'll have two particular combinations of 3 bits, which we won't be using to set the codes, because we never actually use those on our 74 LS381s. But we will be using those to encode certain instructions in our opcodes. And so that's these two, the increase and not, which we assigned to 000 and 111. And so with those operation codes defined here, these 3-bit operation codes, we can now write a macro to construct complete ALU opcodes, because the opcodes for an ALU instruction have a slightly different structure from the opcodes of the other instructions. And so when we want to create an ALU opcode, we have in fact 3 parameters which are interesting for our input. So we have this operation code, which is one of these constants that we define up here. And then we have this this carry flag, which is a 1 or a 0. In fact, it says whether we should take into account the existing carry when performing that operation. And of course, that has meaning for the arithmetic operations. But as we saw in our table, we reassigned some other meaning to that for other operations. But it's a valid bit, which is part of our opcode. And then the 2 least significant bits of our opcode correspond to whatever the first operand is, which needs to be one of the 4 general purpose registers, A, B, C, or D. And so we can then assemble our complete opcode using all of these bits. And so of course, the most significant 2 bits are fixed. Those are 1, 1, indicating we're dealing with an ALU class instruction. And then the next bit is this, whether we want to use the carry or not. That will be bit 5, which is the 6th bit, the 3rd most significant bit of our opcode. And then to the right of that, we will have this 3-bit operation code, for which we've defined these constants. And then so we want those in bit positions 2, 3, and 4. So in fact, we shift that value left by 2 bits, so it will appear in bit positions 2, 3, and 4. And then the final, the 2 least significant bits, well, those will be whatever the register is we want to operate on. And just to make sure that we really are only allowing one of the general purpose registers, we AND it here with binary 1, 1, making sure that really is only 2 bits long. And so by concatenating all of those bits together, well, we can construct an opcode. So we can now have a look at the actual microcode for these ALU operations, which we can now encode into opcodes. And so here is my function to write out all of the ALU instructions. So we start with the simple ones, the increase and the decrease instructions. So those are in fact ALU operations, where we'll encode the operation code using this special value of 000, which we defined. And so the increase will have this carry with carry set to false, and the decrease will have it set to true. And so in both cases, what we'll be doing is we'll need 2 cycles. In fact, almost all ALU operations will need 2 cycles. And in the first one, we'll be writing into this ALU register, and that will be pretty much universal across all of the ALU operations. And in the second cycle, we'll simply be reading out that ALU value, which we wrote in the previous cycle, and writing it into whatever register we're dealing with. And so that's going to be pretty much the same for all of these ALU operations. So they're almost all going to be microcode too. Now in this particular case, for the increase instruction, we've already determined what we need to do. So we have that here for an increase instruction. We need to set the S values to A plus B, and then we need to enable whatever the input register is onto the bus, and we need to disable the ALU B signal, and we need to enable the ALU carry signal. So that should be exactly what this first microcode does. So sorry, for the increase instruction. So we're setting the carry, but we're not setting the ALU B signal, and we're setting the S signals to correspond to this A plus B operation. And then in the second byte, as we discussed, we'll be taking the results which we wrote into that ALU and writing into the register. And so for the decrease instruction, we'll just look at our table here. And so for decrease, what we need to do is we need to set these S bits to A minus B, this operation. Again, we need to enable the register onto the bus. B, we need to disable the ALU B signal, and we need to disable the carry input. So that's what we do in this case. So all we're enabling here is this A minus B, this S0, S1, S2 signals. We're enabling, of course, the register that we want, and we're writing into the ALU register. And so we do pretty much the same for all of the operations in our ALU. So here is the add instruction, for example. And so for an add, we build our opcode in the same way as we always did. So the operation code in our opcode will be a plus b. And so the normal add instruction will have with carry false, and the add with carry instruction will have this set to true. And of course, we need to add the register, which is part of the opcode together with the B register. And so the microcode that corresponds to that, well, we can see that in our table. And so that's here. That's the S0, S1, S2 will be set to A plus B. The A register the register that we're adding to B needs to be enabled on the bus. And then we need to set the ALU B input, in this case, on the ALU. And we should not set the carry input. So that's what we do here. We set the ALU B input, we enable the register which we want to add to B onto the bus, and we set the S0, S1, S2 to the A plus B operation, and we write into the ALU register, and then on the second cycle we read out that value and write it back into the register. Now for the add with carry, what we need to do in fact depends on the current state of the carry flag. And so we in fact have to write a carry conditional instruction, and so if the current carry flag is set to false, then in our microcode we shouldn't set the carry input. And so in this case we're in fact doing exactly the same as in a normal add. We're enabling the register which we want to add onto the bus, we're enabling the B into the B input of the ALU, and we're setting the A plus B operation on the ALU, and we're of course writing into its register. But in this case we're not enabling the ALU carry in. But if the carry flag is set in the flags register, so if there was a carry out from the previous operation, if this is true, then we do set the ALU carry input flag. And so that's how we take care of this situation. For an add with carry, we need to look at the current carry flag to know if we want to set the carry in for this next addition operation. And so that goes for the add operation. Now the subtract operation, in this case it's A minus B, is exactly analogous to the addition operation. So that's almost exactly the same, except that the operation which we're performing is in this case A minus B. And those same 3 bits we'll actually be using in the opcode. And so for the rest, that's an exact copy of that. And so is this. So that too has a subtract and a subtract with carry, but this time the B register minus whatever register we've written in the instruction opcode. So again, this time it's the B minus A operation, but for the rest we have one version without carry. So we'll of course it's a subtraction, so we'll always be setting the carry. But then if we have a conditional on the current state of the carry, then we'll simply be carrying that over. So if that's false, we won't set it, and if it's true, we will set it. So that takes care of all the arithmetic operations, basically. But then we have all of these logical operations, and so the process is exactly the same. So we set our opcode, and so in this case with carry is always false for all of these operations. And then we just look up in our table here what the actual microcode is that we need for those operations. So for an AND, well, we can set A and B, that's an operation which our ALU knows about. We need to enable one of the registers on the bus and set the other one into the ALU directly with this ALU B signal. Of course, carry in is not set. And so that's exactly what we do here for the AND instruction. Again, 2 cycles. In the first one, we'll write whatever this calculates into the ALU register, and then we'll enable the ALU register onto the bus in the second microcycle, and write it back into the register. And so the same for all of these operations. Now, for the logical NOT operation here, there is in fact no native NOT supported by our ALU, but we figured out when we were talking about the ALU that there is a way to set these input signals and to use this B minus A operation with a B input of 0 to actually achieve this inversion of all the bits in the input that's coming in through the bus. And so we can use that to in fact implement our NOT instruction in microcode. And so the opcode which we'll use will be using this special combination of 3 bits, which is 1, 1, 1, which our ALU itself doesn't understand, but that's okay. We can use that in the opcode. And then to implement this instruction in the microcode, we'll just use this combination of inputs that we determined when we looked at the ALU. So we're using the B minus A operation. We're not setting the B input, so that will be 0, and we're not setting the carry, so we will borrow. And of course, it's a real operation where we want to write the result of the inversion back into the original register. And so we have our two steps of microcode: one to write the result of the calculation into the ALU register, and then another to read it out and write it into the final register. And so then we have two more instructions here in the ALU for which we need microcode, and these are the compare and the test instruction. And so these two instructions, in contrast to all of the other instructions we've seen so far, they don't actually write any result back into any of its operands. So the compare instruction compares the value of some register with another register, but it only updates the flags. It doesn't write anything back. And the test instruction, which we just defined, simply tests the value of some register and sets the flags, but it doesn't write anything. And so both of these instructions can in fact be implemented with a single byte of microcode. And so all they need to do is perform some ALU operation. And so once again, we've determined what that operation should be. So for the test instruction, that's this plus with a 0, which will simply set the flags based on the value in that register. And the compare instruction should perform subtraction and then set the flags according to the result of that subtraction. And so both of these instructions, as it turns out, actually only need one extra word of microcode, apart from the fetch cycle. Now we have, in fact, two compare instructions. So just as the subtraction, we can subtract a register from B, or we can subtract a B from a register. And so we support both of those variants of the compare instruction. And so that basically concludes the microcode for all of the ALU operations. So most of them, in fact, use 2 cycles apart from the fetch cycle, so for a total of 4 cycles. But our compare and our test instructions use just 1 cycle. And so as we've done for all the other classes of instructions, so there'll be a few unused opcodes. In this case, there are in fact only 4 of them which we haven't used, and those are the exclusive OR in the operation 3 bits of our opcode with a carry. That would theoretically be what that is. And so that opcode is not assigned, and therefore we implement it using a halt instruction, as we've done for all the other classes of instructions. Now, to have a look at this microcode in action here, I've now loaded a slightly bigger program into our CPU. And in fact, this is a part of the program which I showed you in the very beginning of the series. And this is the part which calculates the power series, or the exponent series, if you like. And so it goes through all of the all of the powers of 2, then all of the powers of 3, of 4, etc. And so at this point in the program, it has just finished calculating the power series of 2. So 128 is the largest possible power of 2, which is smaller than 256. And so at this point, it has detected in these instructions here that the next power of 2 would be in fact larger, would cause a carry. And so it's going to start working on the next power series, which will be 3. And so it's jumped back to this almost beginning of the program here, this label called power next. And so this is where our CPU is located at the moment. So our program counter contains a value of 5. And so we're at time t0, and so we'll start executing the instruction, which is at address 5 here. And now that turns out to be a pop instruction, so we'll have a look at what sort of microcode we might need to execute that pop instruction. So what the pop instruction will do is it will read a value from the stack. It'll take it off the stack and then rearrange the stack pointer here. And then take whatever value was on the stack and put it here in the D register. And so this program uses the stack to keep track of whatever base it's working on currently. So at the moment that we should get a value of 2 in there. And so the idea of this program is to increase that and then put it back on the stack and then start working on the powers of 3. So let's have a look at how this actual pop instruction is implemented. And so as always, the first 2 micro times, T0 and T1, are always the same. So we get this 5 out into the memory address register and then read the instruction into the instruction register. So here it is. And so that is our pop instruction. And so it is indeed a load class instruction. Of course, it's exactly this opcode here. And so we're loading, in this case, into the D register 011, which is a physical register. And we're loading from the source 110, which, as you remember, is the special code we invented to indicate the stack pointer with an automatic adjustment of the stack value after the operation. And so the way the stack works is in fact, it's a series of memory locations which grow downwards. So as we put values onto the stack, these are, let's say, occupied cells into the stack, our stack keeps growing downwards. And so whenever we write a new value in the stack, well, then we'll fill this cell here, and then we'll get ready to use the next one. And so the stack pointer itself always points at the last cell which contains a value. And so when we want to pop a value off the stack, what we need to do is we need to simply use the stack pointer as a pointer into memory, then read out that value, put it wherever we want to store it, and then we should increase the stack pointer so that it then points to whatever the new top of the stack is, and so that's one cell higher. And so in effect we're freeing this cell, and so we will no longer consider its value to be valid, and we'll overwrite it the next time we push onto the stack. And so this pop instruction needs to do two things. It acts as a load instruction, first of all, but at the same time it also needs to increase the value in this stack pointer. And so let's have a look at the microcode that does that. So at the moment the stack pointer contains a value of 3, and so that means that this cell here is cell 3, and so that's the memory address that contains the value that we want to put into the D register. And so this 3 at the moment is being enabled on the bus, and is in fact going to be written into the memory address register. And so far that looks like the first microcode cycle of a load instruction. But in addition, we're activating the ALU here. And so this 3 from the stack pointer, which is out on the bus, is going not only into the memory address register, but in fact is also being processed by our ALU. And as we can see here, what the ALU will do is a 0, 1, 1 operation, which is in fact is an A plus B operation. And so the first operand will be this 3, will be the stack pointer. It's also asserting the carry in flag on the ALU, and so it will add 1 to whatever the result of our calculation is. And the second input is not the B register, because we haven't asserted this ALU B signal. And so the second input will in fact be 0. And so these operations correspond exactly to what we would do if we simply did an increase. But of course this is not simply an increase, because at the same time as this calculation of the value of the stack pointer plus 1, we're also writing the current value of the stack pointer into the memory address register. So we can do all of that on time t2. So all right, let's do that. So this 3 will get, 1 will get added to it, and we'll get a 4 here, but the original 3 will then appear in the memory address register. So there it is. And so now we can do several things. We of course have this 4 here, and we need to get that 4 back into the stack pointer, because at the moment it's in this ALU register. But what we also need to do is to get the actual value, which is in memory, into the D register. And of course we only have one bus, so we need to choose whether we deal with this memory location first, or whether we deal with the stack pointer first. And that's sort of arbitrary, but in this case we've chosen to deal with the stack pointer first. And so the contents of the ALU are at this moment on the bus, and so we'll write those to the stack pointer. But of course this isn't the end of the instruction, because we still need to get the value from RAM, which is now being pointed to by the correct old value of the stack pointer, into whichever register we're popping into, and so in our case that's this D register. So after this cycle completes, after this 4 goes into the stack pointer, we still need to do one thing, which is to get this value from RAM, so we enable RAM, out back into the D register. And so we have the D register write enabled, and so then that too will go here into the D register, and that is the end of our pop instruction. And so in fact that took 3 cycles of our micro time, and so right now we're on time t4, but that will be the end. And so after that we will reset back to time t0, and we'll start executing the next instruction, which is this one. And so there we are. Now that 2, which is of course the base of the exponents we've been calculating so far, is back in the D register, and we're ready to start the next instruction. And so that next instruction is an increase, which we've already looked at once before, and we just looked at the microcode for that instruction. So that is a simple ALU operation. So beginning always the same. Let's go and fetch the instruction. So address in the memory address register, and then the contents of program memory into the instruction register. And there's our increase instruction. So it's a 1-1, that means it's an ALU opcode without taking into account the carry, and this is this special value 000, which we've assigned to the increase operation, and we'll be performing it on the D register, which is value 1-1. So right, D register is being enabled, then our ALU once again is being set to increase, so we have the carry on, but we don't have the B input on, and we're using the A plus B operation, 0-1-1. We'll write it into the ALU register, and that will then write a 3 in there, and then that 3 will go out onto the bus and into the D register with this D write, and that will be the end of the increase instruction. And so then we have a data instruction here. We're going to load this B register with a fixed value of 15, and we'll see in just a moment why we're doing that. So let's just go through that very quickly. So load the instruction, there it is, and so then we need to go and put the program counter into the memory address register again to go and get that 15 from program memory, and then write that into the B register. So there that is. And so now we're ready for this next ALU operation, which is an AND. So once again, let's fetch the instruction. So fetch time t0 and time t1 are always the same. Get that into the memory address register and get the instruction in here. And so our instruction is here in the instruction register now. So it's once again, it's an ALU operation, 1-1. It's not carrying, and its operation code is 1-1-0. And so that happens to be the AND operation, and we're operating on the D register. Of course, second operand is hard-coded to be B. So we want to calculate the AND of D and B. And the idea of that is we're limiting this value to be the least significant 4 bits of this value. And the idea behind this piece of code is we keep increasing this value, and if at some point it becomes 16, then the result of that AND will be a 0. And if that becomes a 0, a base 16 doesn't have any exponents which are smaller than 256, because 16 squared is 256. So after 16, or in fact at 16, we can stop calculating the power series. And so by checking if the result of that AND is a 0, we can figure out if we've come to the end of our power series. And so that's the reasoning behind these instructions. But so okay, let him calculate this AND. So in this case, the result is going to be exactly the same. We'll have 0, 0, 1, 1, and so that will go into the ALU. That happens to already be there, but that's of course a coincidence. And so there it is, and then we'll write that back into the D register. And of course, doing that didn't provoke a 0 because this value is not 0, and so the next jump 0 instruction will not take hold. And so when we load that and put it in here, then we won't actually perform the jump. We'll simply be increasing the program counter to jump over this address here, and then come to the next instruction, which is the push instruction. And so that's the last instruction we'll have a look at. So once again, beginning is always the same. We put the program counter into memory address register and get the instruction in here. So this is the push instruction, which we've encoded as a store instruction. And the destination of the store is this special stack pointer here, so this value of 110, and the value we'll be storing into the memory pointed to by the stack pointer is in register 011, which is the D register, which is this 3. So in fact, we've now calculated the next base, and we're going to put it back on the stack, so that when we finished with this power series, we'll once again be able to figure out what the base was. And so for a push instruction, we need to do the opposite. So in the case of a push instruction, we need to use this empty cell here and fill it up, and then in fact decrease the stack pointer by 1. But of course we need to do it in the opposite order. In this case, we need to decrease the stack pointer first, because at the moment it's pointing at the last occupied cell, and so we need to calculate this address -1, and that will be the address to which we want to store a value. So in this case, we're obviously again outputting the stack pointer contents, which are 4, onto the bus, but we're not immediately writing them into the memory address register, because this 4 is not where we want to write the value which we're pushing on the stack. We need to decrease that by 1 first, and so in this first operation, in fact, we'll only be using the ALU. And so as you can see here, the operation code is 0, 1, 0, which corresponds to A minus B. We have not set the carry flag, which for a subtraction means that we do want to borrow. So we'll be subtracting 1 from the final result, and we're not using the B register, we're using the hard-coded value of 0. And so this means, in essence, it means decrease whatever's coming in on the bus by 1. And so we'll have a 3, and once again, it's actually already there, but really that's pure coincidence in this case. So it will calculate that 3, there it is, and then that 3 will be written finally into both the stack pointer, so that the stack pointer itself has been decreased, but of course also into the memory address register on this time 3 of the push instruction. And so that way we will have at the same time calculated the new value of the stack pointer, and will be immediately pointing the RAM there, so that we can then finally write this value which we are pushing onto the stack into memory, which is where the stack resides. And so on this next rising clock edge, this 3 here will go both into the stack pointer and into the memory address register. And so there it is. And now we're ready for the final microcode on T4 of this push instruction, which is now to write to memory using the input from the register, which we are pushing onto the stack, which is the D register. And so this 3 is now on the bus because it's enabled, and that will be written into RAM at address 3, which is the new stack pointer address. And there we are. And so that concludes the push instruction. And so now we can understand the final part of this microcode program, this Arduino program which generates the microcode for our Arduinos. Remember when we looked at the load and the store instructions, we skipped over the pop and the push instructions. But because we now also understand how the ALU instructions work, we can understand these stack instructions, which are in fact combined memory and ALU operations. And so here we have the pop instruction. And so the way the pop instruction works is a 3 micro cycle instruction, as we saw. And so on the first cycle, we go and get the value, which is currently in the stack pointer. We in fact do everything here to calculate its to increment it by 1 and write the result in the ALU register. But at the same time, we're writing the value of that stack pointer into the memory address register, so that we're also pointing the memory at the correct location, so we can read out the value, which is where the stack pointer is currently pointing, and then at the end of the instruction put it into whatever register we want to pop our data into. And then we need 2 cycles to actually read out the data from memory and to write the new value of the stack pointer back into the stack pointer register. And so the order of these is somewhat arbitrary, and so we chose to first write the result of the ALU increase operation back into the stack pointer, and then on the last cycle we will in fact read out the memory contents, which were located at where the stack pointer was pointing at the beginning of the instruction, into whatever register we want to pop our data into. And so the microcode for the push instructions here, which is part of the store class instructions, so we had a look at that on the CPU just now as well. And so that too is a 3-step operation. So after fetching the instruction, we need to actually decrease the value of the stack pointer, because it's currently pointing at the lowermost full cell of the stack, and so we want to write something into the cell underneath that. So we first need to decrease the current value of the stack pointer, so we enable it, and then set up the ALU here to perform this decrease by 1. And then we write the result of that ALU operation back into the stack pointer, so we're enabling the ALU register. But at the same time, we also write it into the memory address register, because in fact that is the memory location where we will now write the new value which we're pushing onto the stack. And so in the third cycle, the T4 cycle of this push instruction, we'll then finally actually write into memory, which now contains the new value of the stack pointer, and we'll write whichever source register we're in fact pushing onto the stack, so we get the enable signal for that corresponding register. Now remember that in the very beginning of the series, we'd said that we'd like to be able to, somehow get higher level programming languages to compile into code for our CPU. And so here is a bit of pseudo C code. And so the idea is to think about how we're going to implement a function call. And we said at the time that we're going to be using the stack to do that. And so here I have some piece of C code which is executing. There might be instructions in front of here. And so let's assume that for whatever reason this instruction gets compiled into address 12. And so this is a function call. So we want to branch from this execution path here into this function, and then do whatever this function says, and then return back to wherever it is that we called our function from. And so the main idea here is that when we jump to this other location where my function is located, here let's say hypothetically that's at address starts at address 21, we want to first save whatever address we have here. So ideally that would be if this were 1 byte, that would be 13, or if it's several bytes, or whatever the next instruction is after this executes, we want to save that address on the stack, so that we can then, happily go about jumping into this function. And then when we encounter this return instruction, we should simply pop the return address, which we saved on the stack, back into the program counter, and so that would then, in effect, cause a jump back to wherever it is that this function call arranged we should return. So okay, let's see if we can come up with some kind of assembler that would accomplish that. So we said when we call a function, we want to push the program counter onto the stack, and of course if everything goes well, then that program counter at the moment when we actually start executing this instruction will have already been increased to whatever follows this push instruction, because in our fetch cycle we already increment the program counter. So we could do that, and then we can jump to our subroutine, which is here, and then we can execute that, and then at the end we'd want to just get the return address from the stack and put it back into the program counter. The problem with this approach, though, is that of course we will be returning in this case to address 13, because at this moment 13 is what would have been in the program counter, and so we'll in fact return back to this jump instruction, and we'll end up back in our subroutine. So that doesn't work. In essence, what we need is the next address behind this, and so because that particular instruction takes up 2 bytes, that would in fact be 15. And so to do this properly, we don't need to push the program counter onto the stack. We need to push the program counter plus whatever the next instruction is on the stack. And so depending on what kind of jump we're performing here, this could be 1 or 2 bytes more than that. And so it turns out we need to not only do arithmetic to deal with the stack pointer, because this in itself has some arithmetic dealing with the stack pointer, we would need additional arithmetic to deal with the program counter. And if you try and work out some instruction to do that all in one single set of microcycles, well, it turns out you need a hell of a lot more than 8. And in fact, we'd also need some temporary registers. So unfortunately, with my very simple CPU, this approach isn't going to work. And so on my CPU, I'll take a slightly different approach. And so instead of performing the push first, what we'll do is we'll in fact store the address that we want to jump to in some register which we already have. And so I've taken the decision that we'll be using the C register. Once again, we'll be assigning special meaning to the C register for that. And so this is an instruction which the programmer or the compiler of this high-level language will need to write. And then subsequently, we'll simply add some microcode to the push instruction when we are pushing to the program counter. And so if we ever push the value of the program counter onto the stack, well, then there'll be an extra bit of microcode there, which will simply read out the value which is in the C register and then put that as the new value into the program counter. And so by doing that, we will in fact at this point have stored in this case 14, which is the continuation of this function after the function call, onto the stack. And so when we start executing our function here at 21 and come across this pop instruction, which is the equivalent of the return instruction, well, then we will in fact be restoring the value 14 to the program counter, and so we'll continue working on our program here. And so we need to then sacrifice one of the registers which we already have, but so by forcing the programmer to write this, in fact he's perfectly aware of the fact that at this point the C register is needed. And so this combination of microcode will in fact give it a special mnemonic, and we'll call this the call instruction. like this. And so on my computer, we can only ever use the C register as the address to which we are calling. That will be a limitation of our architecture. And so this special pop into the program counter, we'll give that a special name as well. We'll call that the return instruction. But the return instruction really is a pop into the program counter. It doesn't do anything extra. Whereas this is a little bit more than a push of the program counter. It's a push of a program counter onto the stack, and then subsequently a jump to the contents to the address which is located in the C register. And so that's the final bit of microcode that we still need to look at, which is for this call instruction. And so the call instruction is in fact is a push instruction of the stack pointer. So these first three cycles do exactly the same thing as the entire push instruction here. And so the source register in that case would be the program counter. But then when all of that's done, it'll do one final step, which is to move the contents of the C register into the program counter after it's been its previous value has been saved onto the stack. And so that in effect is a jump to the whatever the value is in the C register. And so that's how we'll be implementing the call instruction. And so with that, I think we've now completed our tour of this CPU. So we had a look at the microcode of all the instructions that we currently support, and the program which writes that microcode into these EEPROMs. And then we also looked at the hardware of the control unit here, which is sending out control signals to the computer on all of these yellow wires. We had a look at the ALU and how we're using these 74 LS382 chips to perform the various operations which we support. We looked how that produce flags here, outputs, and also numerical outputs, of course, and we use the bus to transfer that to and from the various registers in our computer. And one of the registers has a more complex decimal display. We of course have a RAM module here which uses addresses and then actual data. And in fact we split our RAM into two parts, into program and data memory. We have an instruction register here which we load based on the programs which we can write into program memory. So yeah, I think we've pretty much covered this entire CPU now. So if you should have any more questions, if there's any part of the operation that still seems unclear or that I may have overlooked, please let me know, write a comment or something like that in this video. As far as I can tell, I think I've pretty much gone through every module on the computer. I think I might like to do one more video which will not talk so much about the implementation of the computer itself, but I think we'll try and see how far we can get in our original goal, which was to see what sort of higher level code. So this of course is assembly code, but we might want to try some slightly more complex algorithm and see if we can get some assembly language that would correspond to that to run on this computer. And so I think I'll do one more episode which will be in which we'll talk mostly about actually programming and using this computer for some more complex operations than we've been showing up until this point. But so do remember, if there's any part of the actual building or working of the computer that you'd still like some information on, well let me know, and perhaps I'll talk about that as well. So anyway, it's been fun, and so as I said, I'll probably see you for one more episode dedicated to actually programming the computer. And apart from that, well, I'll see you one last time.